Welcome to this week's JPS Weekly Product Briefing Webcast. On behalf of JPS and its entire staff, thank you for your business. We thank you for your attendance today. We hope that you and your family are safe and well. I am Carroll Hollingsworth, JPS Vice President of Sales. Iggy Bragado, the JPS Senior Sales Engineer, will provide you with today's program on the SNV 12 voter with API backhaul. The SNV 12 voter is the most flexible, conventional voter on the market today. It's been field proven since 1998. To paraphrase an old quote, it has been imitated, but it's never been duplicated. We are confident that in the next 30 minutes, you will know why the SNV 12 voter with API backhaul is an important solution for many land mobile radio systems all over the United States. Now let's get to the real reason you're here today. Let me introduce Iggy Bragado. Iggy?
Okay, Carol, once again, appreciate it, and I hope everybody is well today. And I'd like to welcome everybody to the JPS Interoperability Solutions Weekly Product Briefing Webcast. I'm Iggy Bragado, Senior Sales Engineer, and as you know, we also have with us Carroll Hollingsworth, our Vice President of Sales. And in this week's webcast, we're going to discuss the SNV12 analog receiver voter, and specifically the IP backhaul solution, which helps support backhaul of received audio over digital networks. We'll learn why this practice has been sometimes frustrating for end users for many years. And the solution is very interesting, especially when GPS or other external timing references are not required. But before we dive into IP backhaul solution, I think we should have a really brief discussion on the essential functionality of the SNV12 voter and the receiver voters in general. This will also help us better understand why voting over digital links can be problematic. So multiple receivers are typically deployed in a region for the sole purposes of establishing greater coverage area, particularly to support subscriber units that exhibit low transmit power. And portable radios are a good example of this. By strategically placing receivers around a region with adequate overlap, you can hopefully ensure that a portable radio user will always be near a receiver that can effectively capture their transmissions. And architecturally speaking, there are lots of variations of a voter receiver systems such as duplex, simplex, multicast, simulcast systems, as well as transmitter steering. But in any case, the use of multiple receiver sites is the basis of the implementation of the voter and comparator. As a subscriber unit moves throughout the region, hopefully its transmissions will be captured by one of the satellite receivers, and in most cases, the transmission from the subscriber unit will be received by more than one receiver, and this is a good thing. The ability to hand off from one receiver to another receiver without disruption is the key to a properly designed system, and this can only be achieved by some amount of overlap. And the job of a receiver voter or receiver comparator is to take the received information from the subscriber unit and deliver that information to a dispatcher or repeat the information back out to the other radio users in the field on the same talk group or channel. But another important duty of the voter is to disguise the handoff of the audio between receivers as the subscriber unit moves further from one receiver and approaches another receiver. The transition of audio between receiver sites of a properly voted system should be completely indistinguishable to the listener. So when a receiver or multiple receivers are in an unsquelched state, meaning they're receiving a transmission from a subscriber unit in a field, a process begins where each receiver delivers its received audio to the voter, and the audio from each site is assessed for quality. And that doesn't mean the loudest, but that means the best in audio quality. And for FM conventional communications, the SNV12 measures the FM spectral noise above 2.2 kilohertz of the received audio spectrum, as you can see in the profile at the bottom left. And then that selects the single receiver that displays the lowest amount of average noise energy. And one and only one site is voted. And incidentally, the SNV12 voter can measure quality based upon the signal to noise ratio, but this is primarily used for AM communications, and particularly that would be air traffic control. But for FM, the SNV12 assesses FM spectral noise above 2.2 kilohertz. And remember, this is going to be important later on when we talk about IP backhaul. All right, so another important element of a properly designed voting system is the method or methods used to deliver receive audio from the remote receiver site back to the SNV12 voter. And I use the word method in the plural tense because there can certainly be different backhaul approaches used in a single voted channel, and we sometimes call that mixed media. So wireline or leased lines have been the mainstay of receiver backhaul for decades. Sometimes they're often deployed and maintained privately, but most are through a service provider. And performance and reliability can sometimes be difficult to predict, and there's always a reoccurring cost factor when using a service provider. There are classes of leased lines that range from voice grade to conditioned grade lines, all of which can affect how the SNV12 assesses FM spectral noise above 2.2 kilohertz. And depending upon the grade of the leased line, spectral roll-off, particularly at the high end, can result in less noise energy arriving at the voter. And remember, if a voter determines a site has less noise energy, it will vote that site, even if that receiver's audio is poor in quality. And in this example of a voice grade leased line, even the actual voice information is poor in quality. The receiver associated with this link will probably be inadvertently voted because of the spectral noise energy is much lower due to the roll-off. This is classic misvoting. And incidentally, the SNV12 contains equalizers that can be instated to correct for this roll-off. And in terms of reliability, most can be affected in terms of performance by the weather, and the lack of maintenance is probably more realization that the service providers are probably favoring their digital offerings. T1 microwave, not digital microwave, we'll talk about that later. T1 microwave is also a popular means of receiver backhaul and exhibits better frequency response than copper leased lines, which means more accurate voting. There is a high initial cost of deployment, but will result in a more reliable and higher performing system without the reoccurring cost factors that we see in a leased line application. And you may notice that I've placed a lot of emphasis on the region above 2.2 kilohertz. We'll see how this can be a really important factor when backhauling over digital links. RF links are often used where microwave is either too costly or too difficult to deploy even leased lines, for instance, over a body of water or a canyon. And technically, there are many ways to deploy an RF link. There can be continuously transmitting links or core activated links, but for the most part, UHF is the frequency band of choice, and the implementation of directive antennas will also help reduce the effects of interference. And RF links are still very common. And since the advent of the NXU2 back in 2000, there have been clever people using JPS RoIP to deliver radio communications over digital networks, and to this day, it's a very common technique. The technology is reliable and cost-effective, especially when using JPS products, obviously, but end users have also used NXUs to backhaul receive audio back from remote receiver sites to the SNV12 voter, which has mixed results. But because of the effects of network jitter and the results of audio compression, voting algorithms are typically unable to mitigate those ill effects of digital backhaul. So for many years, JPS did not advocate the use of RoIP to deliver receive audio to the SNV12 voter. So let's talk about the use of IP networks when deciding to backhaul receive audio between the receiver and the voter. And there's the good and there's the bad when it comes to RoIP and voting. So here we have a very simple 3-site single channel system. And incidentally, the system we see here is a channel. So this single SNV12 voter chassis equates to a single radio channel. There are individual site voter modules within the SNV12 chassis that support the many receiver sites. Sometimes we get confused, but the individual modules are not channels, but sites. So in this example, each of the receive backhaul links are being supported by radio over internet protocol devices that convert the analog receive audio from an analog state to a compressed digital state, which can then be delivered over the network in the form of a UDP packet, which is then received by another RoIP device that decompresses the audio from the UDP payload, which is then converted back into an analog voice information state, and then finally presented to the SNV12 voter for noise assessment. And so there's a lot of things going on. And what makes this so attractive is that an agency can save recurring costs of a lease line, for example. Networks are becoming more and more prevalent, and RoIP is a reliable and a cost-effective way to transport audio over a network. And if you're using JPS NXUs, you have the benefit of a high survivability link, which is essentially self-healing. But like a lot of things, there are also disadvantages. And in terms of a voter, there are two issues related to the network and how voice data is packaged into the payload. The first issue is jitter inherent in most networks. And as you'll see in a moment, the voter can tolerate network latency, but the variation in network latency is the main issue, and we call that jitter. Secondly, the algorithms used to properly package the voice data before it's placed into the payload of a TCP/IP packet, namely the vocoder, has an ill effect on the spectral FM noise that the voter requires to properly assess the quality of the received audio. So again, we have our simple 3-site single-channel voted system with 3 receivers at the right and 3 analog lease line backhaul links in this example. When a receiver is in an unsquelched state, the voter begins to assess the spectral FM noise of received audio from each of the lease line backhaul links. The voter selects a single site based upon quality and sends that audio to the dispatcher or repeats the audio from the transmitter. But in many cases, due to the propagation delay, due to maybe physical distance or devices used to route the audio from the receiver site, some of the audio may arrive later. This too can create a misvoting opportunity, as the voter will interpret the late arriving audio as high quality and then vote that site, when in fact the voter's attempt to assess noise, there is nothing to assess and is perceived as a low noise condition. When in fact, as soon as the late audio arrives, that audio might be poor, and naturally the voter will then switch to a better site, but this still constitutes missed voting, as you may truncate a few syllables in the received audio stream or even cause an echo. However, this isn't really an issue with the SNV12 voter, as receive audio delay can be added to the earlier arriving sites. The early arriving sites will then be buffered in the digital signal processor, and once a late arriving receive audio is delivered, all buffers are then dumped and quality is simultaneously assessed. The nice thing about analog backhaul is that propagation delay usually doesn't change over time. So once the receiver audio delay is provisioned in the SNV12 voter site voter modules, you should not have to make adjustments for literally many, many years, or if ever. So now let's take a look at our original single channel 3-site system, and let's replace the 3 lease line links with 3 digital links. And we can simply use peer-to-peer NXU2A modules, for instance, to convert the analog receive audio to JPS RoIP data. So we're converting analog audio into RoIP, which is then delivered to a peer NXU2A at the voter. Then we recover the analog audio, which is then presented to the associated site voter module. And just like our previous analog backhaul example, we may notice certain links are exhibiting propagation delay or process delays. And in this example, this is the case. Because we can adjust the receive audio delay of each separate site voter module, we can then buffer the early arriving receive audio and wait for the late arriving audio to arrive. Again, we're able to align the arrival time of all receive audio such that each side is assessed at the exact same moment. But later in the day, I might receive a call from dispatch reporting a voting issue, and lo and behold, my previous receive audio delay adjustments are no longer valid, as the network latency has changed over time due to saturation. Again, this variation of network latency over time is what we call jitter. And because network latency is will breathe throughout the day due to loading during the workday, for instance, and desaturating after hours, there will be misvoting issues throughout the day. And this is totally unacceptable. Another issue that is exhibited in an IP network backhaul situation is related to the vocoders used to digitally compress the receive audio that is placed in the payload of a packet. Vocoders are essential in conserving not only network bandwidth, but maintaining the fidelity of the receive audio in this case. Vocoders are using sampling and quantization techniques to apply digital values for tonal and frequency properties of the analog audio. And unfortunately, vocoders inherently will not preserve noise. Sometimes certain tones and frequencies, and these might include the pilot tone, the status tone, or even the guard tone or idle tone. So quantization error of the recovered analog audio presented to the site voter module will have compromised the FM spectral noise that is so important in the SNV 12 voting criteria. And because the spectral noise has been reduced due to the vocoders, the voter will tend to vote those sites even if the voice audio is poor. Right? So you may have noticed we place a lot of emphasis on timing and noise, and for proper voting to occur, all receive audio must arrive at the voter at the same moment, and there must also be noise present to properly assess the quality of the receive audio. And so as you know, the vocoder could be an issue. And backhauling receive audio over networks can't be taken lightly. Okay, so let's look at a couple site voter module options that we do offer. And this is the SVM2 site voter module, the analog site voter module that populates one of the 12 slots at the right of the SNV12 voter chassis, as you can see on the bottom left. It will support a single transmitter receiver site and will backhaul analog links over leased line, copper tie lines, T1 microwave, and RF links. And what we learned about TCP/IP networks, we want to avoid any form of digital transport when dealing with receive audio using the SVM2 analog site voter module. And incidentally, you can stack 3 voter chassis together to support up to 36 analog receiver backhaul links. In that case, the 3 stacked voter chassis will constitute a single radio channel. So just remember that. The SVM2 contains a digital signal processor that is used to assess the all-important spectral noise, as well as contains the receive audio delay buffers that help align the arriving receive audio. There's a lot of things going on in this module, and maybe we'll save that for another webcast. This is the SVM3 digital site voter module. It also slides into the SNV12 chassis. A couple things you might notice is that there is an Ethernet port on the faceplate, and you may have also noticed that there is 3 of everything, selector switches and status LEDs. But unlike the analog SVM2, the SVM3 will be able to support 3 receiver transmitter sites, as you can see in the upper right-hand corner. So if you were to fully populate a single SNV12 chassis with 12 SVM3 digital site voter modules, you'd be able to support up to 36 receiver sites in a single chassis. And you can even stack 3 chassis together for a multi-chassis solution to support up to 60 sites. A module that works in conjunction with the SVM3 digital site voter module is the QMT1B module. The QMT stands for Quality, Measurement, and Transport. This module is co-located at the receiver site, and this allows for the immediate capture of analog FM spectral noise prior to compression of the received audio in the form of RoIP. And once we've captured the FM spectral noise value, it's then expressed as data, which is lossless, and it is delivered to the control processor module for comparison with the spectral noise captured by other analog SVM2 and QMT1B modules associated to this channel. And remember, the SVM3 will be able to support 3 QMT1B modules at 3 different sites. Now that the vocoder audio fidelity issue is solved, remember, we've captured the spectral noise at the receiver. The modules can now work together to mitigate the effects of network jitter. And remember, the SNV12 voter can handle the latency, but not the jitter, right? So we can handle the latency, but we cannot tolerate the jitter. So as you can see in this example, the SNV12 voter can be populated with both analog SVM2 and digital SVM3 site voter modules. And this is truly a hybrid solution. And we'll talk about this a little bit later. The CPM3 control processor module periodically issues an internally generated timestamp that is shared with all SVM2, SVM3, and QMT1B modules. The time sync occurs at a rate of every 60 seconds and can be adjusted between 0 and 90 seconds. And this effectively is virtually resetting the internal clocks of all modules every 60 seconds, but also provides a timestamp reference with respect to unsquelched events that might occur when a receiver begins receiving. The voter is continuously assessing the virtual path length of the digital links, even as the network breathes throughout the course of the day. And when an unsquelched receiver event occurs, analog SVM2 modules, the analog modules, begin assessing their audio from their assigned receivers, as well as the QMT-B modules co-located with the receivers do the same, all capturing the FM spectral noise of their respective receivers. And as the receive audio at the remote QMT1B module is being assessed, compressed, and prepared for delivery by way of UDP network packets in the form of RoIP data, the CPM3 control processor module within the chassis will command receive buffers in the SVM2 and SVM3 site voter modules to begin filling their internal buffers. The amount of audio to be buffered is based upon the instantaneous timestamp at the moment the site transitioned into an unsquelched state. So we're forcing early arriving receive audio to be stored in the internal digital signal processors, which are the buffers, to wait for the late arriving receive audio. The audio buffers will then breathe as the network latency changes throughout the day. And once the last site checks in with its time sync, the modules then dump their buffers, and we simultaneously measure and assess the receive audio quality equally across the board. So we've effectively mitigated the effects of network jitter and the effects of the quantization error upon the receiver's FM spectral noise. And most importantly, this solution does not require GPS or external timing references. No bolt-on solutions, but everything is done internally. There are two quality measurement transport backhaul modem models, and the QMT1B IP backhaul modem will support a single channel at a single site and has a 4-wire receive and transmit audio interface. It also will accept either an active high or an active low core control signal from the receiver. It'll also accept 2175 hertz or 1950 hertz pilot tone. It also contains a remote controllable receiver and transmit audio pots. This means you do not have to visit the receiver site to adjust the receive and transmit audio levels, which is very convenient. And the QMT1B is also E&M capable on the transmit side. And as you can see, a single SVM3, as we mentioned, will support up to 3 sites when incorporating QMT1B modules. So if you choose to add one more site in this example, we will need to add a single QMT1B module out at the receiver site and an additional SVM3 site voter module within the chassis. We offer a QMT-R, which is a rack-mountable IP backhaul modem that will support up to 4 channels per site. The QMT-R can be ordered with 1, 2, 3, or 4 installed modems. This is certainly a better way to be space and power efficient than deploying discrete QMT1B modems. So depending upon your application, you may need to deploy both multi-channel QMT-R and single-channel QMT1B modems. And additional IP backhaul modem modules that slide into the QMT-R housing can be ordered to be later installed as the system grows. And by the way, the QMT-R modem can also be powered with 48 volts telco. Just to clarify what a single QMT-R looks like in a very simple system, this is an example of a 4-channel, 3-site system. And as you can see, a single SNV12 voter chassis at the left is supporting channel A in this example, and there is a channel A receiver at each of the receiver sites. And there are lots of numerical options in terms of channels versus sites, and we can certainly work with you to architect a system that is very hardware efficient. So give us a call if you're interested in talking about the variations in terms of hardware in a system such as this. Again, but what's important is that the QMT-R is really very space and power efficient. All right, so one thing I wanted to mention in terms of existing SNV12 voter systems is the IP backhaul solution is not a forklift solution, right? In terms of going from an analog receiver backhaul system to a fully digital backhaul solution, this is not the case. Analog SVM2 and digital SVM3 modules are designed to coexist in the same channel, which is the chassis. And this means you can replace a single lease line, for instance, with a fiber link and retain your existing analog backhaul links at the same time. You'll be able to vote analog and digital links at the same time. So this is a very cost-effective solution in terms of migrating slowly to an eventual total digital backhaul architecture. Right? So I'd like to thank all of you for joining the webcast today. And if you need more information regarding the SNV12 analog receiver voter and are interested in backhauling your receiver audio over digital links, you can always give us a call directly or visit our website at jpsinterop.com. And Carroll, do you have something you want to close with?
No, I appreciate everyone attending today. Excellent questions. Thank you so much for those. Thank you for your participation. We look forward to seeing you on the next Wednesday's webcast on the new NXU2B. That will be a very good presentation. Look forward to seeing you then. Thank you very much. We hope you stay safe and have a good day.
Okay, everybody, thank you. Appreciate it. Thank you, everybody.